Please join me in welcoming Sivan.
Thank you. Hi, everyone. Thank you for the opportunity to give this keynote at Flash Memory Summit. I know we are a relatively small and young company compared to NetApp, so it certainly set the stage for the innovation we're going to show you. So throughout Flash Memory Summit, you've heard a lot about NVMe over Fabrics and NVMe technologies in general. But we are going to talk more about the who, why, and how of NVMe over Fabrics. Who is using it, why do they have a need for it, and how they use it. So we see today a lot of market verticals that are attacking, that have a need for NVMe over Fabrics. We run into it a lot in financial customers, in large websites and retailers, in high-performance computing, and in infrastructure as a service deployments. Some of the applications include real-time analytics, where it could lead to faster time, reducing the time to results. Transactional processing, like SQL and Oracle databases, are still kind of bread and butter databases that require faster processing times. Business intelligence, machine learning algorithms can all benefit from faster storage. And finally, in the hyperscale data centers, we see a need where scalability of storage without sacrificing of performance is a key feature requested. So who would really need it? Anybody who uses today local SSDs would benefit from NVMe SSDs. And it's ideal for SQL and NoSQL databases and for high-performance distributed key-value stores. But what's even more interesting about NVMe and NVMe over Fabrics is that it enables new applications like machine learning, Internet of Things databases and analytics. Think about all the sensors that collect information for Internet of Things. All that data needs to be collected somewhere and then needs to be analyzed and acted upon. Real-time application performance monitoring. Think of point-of-sale devices that collect information from the many branches of a large enterprise. Again, all that data is collected somewhere, and decisions need to be taken on that data as fast as possible. Real-time security audits, another example we run into, where sensors monitor, be it physical security or computer and network security. All the sensors collect that information, again, into a database. Imagine the importance of running an audit within 30 minutes rather than overnight to determine that there was a breach in security, be it physical or via the network. So today, we see that storage growth is really growth in data rather than growth in infrastructure like it was 5 years ago when I was at IBM XIV, where most of the growth we saw was in physical to virtual migration of servers. And one example we ran into, which I think everybody can relate to, is a big retailer website that probably most of us use. They say that their business volume only grows 5% a year, which makes sense, but at the same time, the size of their database actually grows 60% a year. And the performance requirements on that database grow by 100% a year. And why is that? Our queries on their database become ever more complicated and multidimensional. And we hit the database a lot just making up queries to see if we want to buy something, but we don't really end up buying it, but we keep getting all these requests. The requests themselves are also data that that website collects about us. And imagine how important it is to find out that there is a public interest in a certain product or a certain travel destination, that interest is growing right now. That could serve as data that they can sell on to the manufacturers of that equipment. So what started the 8 was when we saw that the following contrast. SSDs are becoming faster, and this chart merely captures the data sheet of a 2009 era SSD. At the time, that was SATA, a 2012 era SSD, that was SAS, and a 2015 SSD, which is NVMe. And the numbers just speak for themselves. The throughput and bandwidth keep growing. There's actually an explosion in throughput and bandwidth in NVMe, as we all know, and the latency keeps dropping. But at the same time, the performance of an all-flash array has lagged behind and is not being able to keep with the performance of an NVMe drive. And this is the same comparison, the data sheet of an NVMe drive, compared with the data sheet of an all-flash array with 2 controllers and 24 SSDs. As you can see, a single NVMe drive can do 2 to 3 times the performance of today's all-flash arrays, exceeds it in bandwidth, and has 5 to 10 times lower latency. And why is that? What we've seen in all of today's existing all-flash array architectures is a very similar phenomenon. The architecture is limiting the performance you can get from the underlying SSDs by a problem which is a classic scale-up bottleneck. All the data that goes from customer servers to the SSDs is piped through typically 2, sometimes 1 controllers, and it's those controllers that constitute as the bottleneck of the architecture. And the stronger the controller, the more performance you get, which is exactly the definition of a scale-up bottleneck. So sometimes people say, well, if I compare local SSDs or NVMe SSDs to all-flash arrays, it's not an apples-to-apples comparison, which it's true, it's not. An NVMe SSD is just a device about the size of an iPhone, and an all-flash array is a pretty large and expensive component. But if you think of it from the eyes of a customer, it is a fair comparison, because at the end of the day, either they're going to buy local SSDs to run their application on, or they're going to buy similar capacity behind an all-flash array to run the application on. For them, it's an either-or decision, and the comparison is fair. Inevitably, what we see happening in the market is that more and more customers choose to use SSDs as local storage. So what is the problem with that? Maybe using local SSDs as storage is the perfect solution. And we all hear about NVMe over fabrics, but what is the problem that really solves? So basically, there's 2 problems here that we're going to describe quickly. One is the provisioning problem. Local SSDs create many islands of storage. Those islands are only accessible by the server that those SSDs reside on. That, in turn, leads to capacity utilization inefficiency. On average, local SSDs are only 20 to 30% utilized. That's the kind of numbers we hear from customers and from large data centers. Another problem is you cannot share SSD content between servers. And another problem is that growing your capacity is either very awkward or, in some cases, completely impossible. A different set of problems is the coupling of storage and compute. And one of such problems is that you need to buy upfront all the SSD capacity you want for that particular server. So not only do you need to buy it in today's prices, you're basically committing to a certain level of capacity that you don't even know if you're going to consume, and you're paying for it in today's pricing, which typically drops 20 to 30% every year. So by postponing that purchasing decision, you could actually save a lot of money. Another problem is that repair and upgrade of your compute or your storage affects the other one. And finally, the lifecycle decision is a big problem that often gets hidden under the rug. Typically, servers get phased out of the data center after 3 or 4 years due to the TCO argument that the new servers, or Moore's law, lead to such efficiency that it's better to buy new servers and throw the old ones out. But storage in the data center typically lives for 5 or 7 or even more years, especially with SSD that doesn't suffer from the same problems of hard drives. So what is the solution? And this is where NVMe over Fabrics comes into play. And E8 storage is an end-to-end NVMe over Fabrics solution. This is actually the data sheet of E8 Storage's 100 gig NVMe over Fabrics solution with 10 million IOPS of 4K read, including our RAID 6 implementation, over 40 gigabyte a second read bandwidth, and slightly higher latency than using local NVMe because obviously it's remote on the network. As you can see, you can finally get the true performance of the SSDs that you're sharing. Now, to do a full solution of NVMe over Fabrics, in our opinion, 3 things need to happen. One is you need to keep performance on par with the local SSD. Otherwise, you've ruined the whole purpose of using such fast SSDs in the first place. The second problem is you've just created a huge blast radius, and we're seeing here solutions being announced that can be even 1 petabyte with a single point of failure. So imagine what happens when that box gets a single failure. You basically lose access to 1 petabyte of data. Today's shared storage solutions typically use high availability to ensure that you don't lose data or loss of access to data due to a single failure. E8 is the first highly available NVMe solution in the market, and we believe these are table stakes to get 1 petabyte boxes in deployment. The third thing you would need is to have some sort of value add or value proposition on top of using local SSDs. If at the end of the day all you did is move the SSDs from one point to another, the value proposition is pretty weak. And we have features like shared writable LUNs, RAID 6, and dynamic provisioning that give the customers a value to having shared SSDs and disaggregate them from the servers. So our theme for the show was actually a game of Luns, and unfortunately, no one could see the actual booth because the exhibit was closed. But I wanted to give you this example of a customer use case, and why we called it a game of Luns. You're going to see in a second. So this customer, it's a financial customer in New York. They have a 10 terabyte data set. And when they try to, the computation requirements on that data set are far larger than a single server. In fact, they have clusters of about 70 or 80 servers that all access the same data. And when they try to share that in a SAN or an S array, the latency that they measured was between 1 millisecond to 2 milliseconds, because that's today's all-flash arrays. So what they ended up doing is literally buying local SSD capacity of 10 terabyte, actually 16 terabyte, for every single server in the cluster. And they copy the data over 70 times. And whenever the data gets modified, they broadcast those changes to all the nodes in the cluster. And that was far more cost effective for them, and that's how they were able to achieve the low latency of local SSDs. What E8 has done for this customer is allow them to consolidate from 70 SSDs to 1 SSD by having it all shared in a single box of shared NVMe. The performance of NVMe is so high that we could provision and dish it out to 70 servers connected concurrently to E8. The performance that the customer actually measured was 125 microsecond average latency from his applications through the network to the E8 shared box. And that's why we called it a game of Luns. Another example that we just published is with Tel Aviv Stock Exchange. So E8 is an Israeli company, and I'm from Israel, obviously. And one of our customers there is the Tel Aviv Stock Exchange that had a problem that they figured only storage class memory could solve. The requirements on the real-time trading system were so high that even NAND SSDs were not fast enough to keep up with it. So they ended up with doing an in-memory solution. But again, that leads to very awkward deployment, roughly 1 terabyte in every machine, very expensive, a lot of power being consumed, a lot of real estate being taken up. And this customer literally reached out to E8 after seeing our presentations on the internet. And we've always said that we could support any 2.5-inch NVMe SSD. And when Intel came out with their Optane SSDs, they reached out to us whether or not we can share Optane SSDs in a similar fashion. And lo and behold, that's how this project came to be. And we provide them much lower latency than NAND SSDs. Now, the question that we asked them was, how can Optane really replace RAM? The latency of RAM is far lower than Optane. And the answer was that because it's a clustered application, the true latency that they get in their cluster was 2 to 3 network hops over 40 gig InfiniBand, which is roughly 20 microseconds, which is roughly what Optane would give them. And in the E8 architecture, it only goes through 1 hop over 100 gig RDMA network. So shared Optane was able to displace a RAM cluster if you measure the network hops in between, and we found that to be a very interesting use case. So regarding hyperscaler usage deployment, the problem with using local SSDs, if anything, is that they're not full or not being fully utilized. By moving to a shared or disaggregated consumption model, you can save a lot of money by postponing the decision of deploying storage to when you actually need it. Based on the calculations that we did with a certain customer, we realized with them that this could lead to a TCO reduction of 62% just by the fact that you postpone the purchasing decision to when components are actually needed, if they're needed at all, and to the price point of that componentry in the future. And that could save over $50 million for a 5-year life cycle of a data center. This is another depiction of that problem. They start with 96 servers in the rack and a certain level of SSDs in every server, and they end up with slightly less servers, 92 servers in the rack, but the utilization of the SSDs now is 88%. So one of the trickier aspects of NVMe over Fabrics is the networking, of course. And this is something we have found to be challenging, and one of our claims to fame is being able to support a converged network. And what does that mean? So we've come to an age where after dominance of fiber channel for a very long time, today customers can get very cost-effectively 100 gig Ethernet ports that actually cost 3 times less than what they would pay for 32 gig fiber channel ports. And it really means that there's hardly any point now to deploy that kind of equipment when you have 100 gig anyway. And if you have 100 gig anyway for your background traffic, and 100 gig is certainly sufficient for your storage traffic, what is the purpose of overlaying 2 networks, one on top of the other? Why not run everything in a converged network? And that would mean that you can save NICs or HBAs in the servers themselves. You can save cabling going between those NICs and HBAs to the switches. And you can save the fiber channel switches or routers or PCIe switches or routers or very complex back-to-back solutions like we've seen, for example, in EMC DSSD. All of this can be replaced with a single top-of-the-rack storage solution which connects directly to the top-of-the-rack Ethernet switch. And E8 is such a solution. To deploy E8, it's nothing more than unpacking the box, racking the box, the unit into the rack, and connecting it to the top-of-the-rack Ethernet switch. That's all the deployment. From that point on, you are basically in the network, and you can connect to all the servers in the network. And I'll explain in a second about the rack scale versus network scale distinction. Now, to support a converged network, you need to do a lot of magicry around network quality of service. And this is a big part of what E8 does in its software to make sure that storage traffic does not interfere with the general traffic and that the general traffic does not interfere with the storage traffic. So when we started out, we called ourselves Rack Scale Flash because it is far simpler to deploy NVMe over fabrics in a rack scale environment. You don't need to deal with inter-rack links, and you don't need to deal with the more complicated configurations that entails. So instead of going to customers and telling them, we are a network scale flash, but your network sucks, so we're only rack scale in your environment, we flipped the argument around. Today you use local SSDs, that's server scale flash, and we open the door for you to use rack scale flash. But in reality, E8 connects directly to the Ethernet network, and by definition, it is a network scale architecture. However, there is a few things that need to take place, both from the customer perspective and from the E8 implementation for that to occur. One is they need to have pretty thick inter-switch links, which was not the case until now. But now with the advent of 200 gig and 400 gig technologies, it will be much simpler to create these kind of inter-switch links that will allow NVMe over fabrics to run smoothly from one end of the data center to the other end. The second thing is the RoCE, or RDMA over Converged Ethernet. And there are certain enhancements in RoCE that enable a network scale deployment. One, for example, is RoCE v2, which allows for routing of RoCE between layer 3 domains. Another is early congestion notification, which reduces the need for pausing, which is could be a problem in very large scale. And these are techniques that we have started deploying in customer POCs to show that there is a network scale option for RoCE and for NVMe over fabrics. From the E8 perspective, features that we've added to support this, one is what we call on-demand storage. You can easily add NVMe capacity now to E8 boxes, either by starting off with a partially populated box and adding SSDs to it, or starting off with one box and adding entire boxes to it. This is a feature we just announced this week. The other is managing at cluster scale, at network scale, which means that you can manage all of your E8 boxes as a single entity, and you don't need to manage them as islands of storage anymore. And these are the enablers for the network scale deployments. So quite often we are getting the questions of, can you actually show us the performance? The numbers seem too good to be true. The most common reaction we get to our presentation is incredulity. It just doesn't make sense. How are you able to get from commodity hardware such high performance that is 10 to 40 times what similar products are getting? And so after getting through the presentation, we have a product demo, and still the reaction is incredulity. It is very hard to explain to people how that is done. But this is the actual data sheet of E8 on a 2U24 box with a RAID 6 implementation. We clock under 500 microseconds for almost the entire range. Up to 5 million IOPS, you get even something like less than 300 microseconds. It truly does reflect the underlying behavior of the SSDs. And this is with NAND SSDs. As you go into storage class memory, you would get even higher performance. The system itself peaks at around 10.5 million IOPS per second. This is a 4K random read workload, and it shows you latency versus IOPS. The other workload that is commonly measured is, of course, bandwidth, and we peak at about 45 gigabytes a second. And again, this is 10 to 20 times the bandwidth that we've seen other all-flash arrays in production today advertising. If you mix the workload and an 8K 90% read, which is very typical for many databases, the performance is, of course, slightly lower as we have 8K IOs, and the writes performance a bit lower than reads. But even including our RAID 6 implementation, look at these crazy numbers. At 3 million IOs of 8K with 90% read, 10% write, you only touch 500 microseconds. Every customer we show this to is simply shocked. We hired an Oracle DBA that after setting up Oracle, he came to us and said there is something wrong in the configuration, and he shows us the numbers, and when you tell him, no, it's not wrong, that is the actual performance of the system, and he was just stunned beyond words. It was literally more than 10 times faster than Tier 1 systems that he was installing for his customers before that. So finally, E8 storage, rack scale flash, no compromise. We get the best of breed performance by using NVMe SSDs, and now the advent of Optane SSDs allows us to get even higher performance and lower latency and more consistent latency. We have best of breed reliability by, at the end of the day, selling a no point of failure, highly available centralized storage appliance. We get best of breed scalability because we scale through the customer servers, and even our initial deployments have over 100 servers mapped to a single E8 box. And finally, E8 is extremely affordable and cost-effective. We only use off-the-shelf commodity components. There is no crafty hardware or FPGAs or firmware customization. We work with all the major SSD vendors, network vendors, and enclosure vendors to guarantee that kind of innovation that they do can be used by us and rolled on to our customers. That's it. Thank you very much.